NASA pointed out their most powerful instruments toward the very edge of existence, and they discovered something that fundamentally changed not just our understanding of the physical universe, but our understanding of what it means to know anything at all. At the farthest reaches of what we can observe, roughly 46 billion light-years away in every direction, there exists a boundary beyond which light itself can never reach us. This is not merely a limit of our technology or our telescopes. This is the edge of everything we can ever know about the universe, a cosmic event horizon where galaxies are receding from us faster than the speed of light itself, and any light they emit right now will never, ever arrive at Earth. And with that light goes all information, all possibility of knowledge, all chance of connection. Think deeply about what this means. There are events happening right now, at this very moment, in regions of space that have crossed beyond our cosmic event horizon. Galaxies are forming, stars are being born, planets are coalescing from dust. Perhaps life is emerging, consciousness awakening, civilizations building their first telescopes and looking out at their own observable universe, asking the same questions we ask, wondering if they are alone. All of this is happening, is real, is part of the same cosmos we inhabit, yet we can never know about it. No signal they send will ever reach us. No light they emit will ever touch our detectors. They exist in a realm that is not just distant, but fundamentally, permanently, absolutely unknowable to us. This creates a profound epistemological crisis at the heart of cosmology. We pride ourselves on the scientific method, on empiricism, on basing our knowledge on observation and evidence. Yet here, we confront the limits of that approach. There are true facts about the universe, events that are genuinely occurring, phenomena that are absolutely real, yet which can never be observed, measured, or verified by us. The universe extends beyond the boundaries of possible knowledge. Reality is larger than what can be known. This is perhaps the most humbling realization in all of science. We have reached the edge not just of space, but of knowability itself. The discovery of this edge came through decades of patient observation and technological breakthroughs that allowed us to see deeper into space and further back in time than ever before. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, created three-dimensional maps of millions of galaxies, revealing not just where they are, but how they are distributed across the cosmos in vast cosmic webs and enormous voids. These maps showed a universe that looks like a gigantic sponge, with galaxies concentrated along filaments and sheets surrounding vast empty regions, where almost nothing exists. But these maps did more than show us the present structure of the universe. They showed us how that structure came to be, how it is evolving, and where it is going. By looking at galaxies at different distances, which means different times in the past, because light takes time to travel, astronomers could see how the expansion rate of the universe has changed over billions of years. And what they found was startling, shocking even. The expansion of the universe began accelerating about 5 billion years ago, and this acceleration has been increasing ever since. This discovery earned its discoverers the Nobel Prize, but more importantly, it revealed that we live in a universe that is tearing itself apart, slowly, inexorably, and permanently. This acceleration is driven by something called dark energy, a mysterious force that permeates all of space and seems to have a repulsive gravitational effect. Dark energy makes up about 68% of the total mass and energy content of the universe. We do not know what it is. We do not know why it exists. We do not even know if it is truly constant or if it might be changing over time. What we do know is that it is winning the cosmic tug-of-war against gravity, pushing the universe apart faster and faster. This means that galaxies near the edge of our observable universe are already receding faster than light. We can still see them, but only because we are observing light they emitted billions of years ago, when they were closer to us and the universe was smaller. Any light they produce now will never complete the journey to our telescopes. They have crossed what scientists call the cosmic event horizon, becoming forever unreachable and unknowable. With each passing moment, more galaxies cross this threshold. The observable universe is not growing larger, as we might expect, as light from more distant regions reaches us. Instead, it is shrinking. We are losing galaxies to the accelerating expansion, watching them slip away into a realm beyond all possible contact. The Planck satellite mapped the cosmic microwave background, the afterglow of the Big Bang, with unprecedented precision. This map reveals the universe's composition. About 5% ordinary matter, 20% dark matter, 75% dark energy, the stuff we are made of, 27% dark matter, invisible particles that interact only through gravity, and 68% dark energy, the mysterious force driving the acceleration. That dark energy percentage is growing, meaning the acceleration will only get worse over time. Future projections are sobering, even terrifying in their implications. In about 100 billion years, all galaxies outside our local group will have passed beyond the cosmic event horizon. The local group itself, the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies, will merge into one giant elliptical galaxy. This merged galaxy will float alone in an empty, dark universe, with no other galaxies visible in any direction. Imagine standing on a planet in that far future galaxy and looking up at the night sky. You would see stars, certainly, billions of them, but beyond those stars, nothing. Just darkness. No distant galaxies, no cosmic web, no evidence that anything exists beyond your own island universe. Future astronomers in that era might never even know that other galaxies exist or that the universe is expanding, because all the evidence will have vanished beyond the horizon. This is not speculative science fiction. This is the inevitable consequence of measured physics. The Baryon Oscillation Spectroscopic Survey has traced how sound waves in the early universe created a characteristic scale in galaxy clustering. By measuring how this scale appears, stretched at different cosmic distances, we can trace the expansion history and project it forward. Every measurement confirms the same dark future. Every refinement of our observations makes the picture clearer and more certain. The universe is pulling itself apart, and there is absolutely nothing we can do to stop it. Imagine standing on a beach and watching boats sail away toward the horizon. Now imagine that the ocean is expanding, carrying the boats away faster and faster. Eventually, some boats cross a threshold. They are moving away so fast that even if they fired a signal flare, the light from that flare would never reach you. It would be carried backward by the expanding ocean as fast as it tried to travel forward. Those boats have not just sailed out of sight. They have sailed out of existence as far as you are concerned. They might as well be in another universe entirely. This is our situation on a cosmic scale. We are watching an exodus of galaxies, a permanent separation of parts of the universe that were once in contact and could once have influenced each other. The universe is fragmenting into causally disconnected regions that can never again communicate, never again exchange information, never again be part of each other's story. This fragmentation is not a future possibility. It is happening right now, at this very instant, as you read these words or hear this voice. Every second, thousands of stars pass beyond the cosmic event horizon, lost to us forever. and there is absolutely nothing we can do to prevent it. The cosmic event horizon is currently about 16 billion light-years away. Galaxies beyond this distance are already unreachable. They are receding faster than light, and nothing we could ever send, not even a beam of light itself, would catch them. This horizon is shrinking in what astronomers call co-moving coordinates, meaning fewer and fewer galaxies remain within our potential reach. Every year, about 20,000 stars pass beyond this horizon. 20,000 suns, with their planets, their potential for life, their stories and possibilities, gone from our universe forever. The European Space Agency's Euclid mission, launched in 2023, is designed specifically to study dark energy. Its observations of billions of galaxies will refine our understanding of cosmic acceleration. But every refinement so far has only confirmed the basic picture. Every new measurement has made the future seem darker and more isolating. The universe is pulling itself apart, and we are powerless to stop it. We can only watch and document and try to understand why. The speed of light is not just a speed limit for matter and energy. It is the speed at which information can travel, the rate at which cause and effect propagate through spacetime. This creates what physicists call light cones, which are regions of spacetime that can influence each other. Events outside your light cone cannot affect you, and you cannot affect them. This fundamental structure of reality means the universe is naturally divided into regions that are causally disconnected from each other, separated not just by distance, but by the very fabric of space-time itself. Consider what this means for the concept of the universe as a whole. We speak of the universe as a single entity, a cosmos, from the Greek word meaning order or harmonious whole. But is it really one thing if parts of it can never interact with other parts? If there are regions that are permanently beyond each other's ability to influence or even observe? The universe may be more like an archipelago than a continent, a collection of island universes that share a common origin but are drifting apart into eternal isolation. Each island is complete unto itself, with its own galaxies and stars and perhaps civilizations, but forever cut off from all the others. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light-years. But there is almost certainly more universe beyond what we can see. In fact, if current theories about cosmic inflation are correct, the total universe might be vastly larger than the observable portion, possibly even infinite. This means there could be countless other civilizations out there, separated from us not just by distance, but by the fundamental structure of space-time itself. Think about the profound loneliness this implies. There might be other beings right now, at this very moment, looking up at their night sky and wondering if they are alone in the universe. They might be asking the same questions we ask, developing the same physics and mathematics, making the same discoveries about the nature of reality. They might have discovered the cosmic event horizon just as we have. They might understand that they are isolated, cut off, forever alone in their corner of existence. They might even have detected signs that there are other galaxies beyond their cosmic horizon, other regions of space they can never reach or observe. But we will never know about them, and they will never know about us. We are like messages in bottles, floating in an infinite ocean, each surrounded by a bubble of possible communication that is shrinking with every passing moment. Even if they somehow developed faster than light travel tomorrow, even if they found a way to bend the rules of physics that we believe to be inviolable, we might never encounter each other because we are outside each other's light cones. The cosmic event horizon is not just a barrier to communication. It is a barrier to existence itself, at least to existence in any sense that matters for possible interaction or knowledge. Two consciousnesses, two civilizations, two entire galaxies full of life and meaning and purpose can exist in the same universe and yet be completely, utterly, permanently invisible to each other. This raises profound philosophical questions about the nature of existence and reality. If something exists but can never in principle be observed or interacted with, in what sense does it exist for us? Does a galaxy beyond the cosmic horizon exist in any meaningful sense if no information from it can ever reach us? The pragmatist might say no, that existence requires the possibility of interaction or observation. The realist might say yes, that things exist independently of whether we can know about them. But this is not just an abstract philosophical debate. It has real consequences for how we understand our place in the cosmos and what it means to know anything at all. The techniques that revealed this edge of everything involved pushing the boundaries of what telescopes could detect. Infrared astronomy played a crucial role because dust throughout the universe blocks visible light but allows infrared wavelengths to pass through. This became especially important when studying the center of our own galaxy, where thick clouds of dust obscure our view in visible light. In a way, visible light shows us a filtered, incomplete picture of reality. It is only when we expand our senses beyond the visible spectrum that the full truth begins to emerge. This is a metaphor that applies more broadly to human knowledge and experience. Our direct sensory experience gives us only a narrow slice of reality. We see a small range of electromagnetic wavelengths, from red to violet, maybe 700 nanometers to 400 nanometers. But the electromagnetic spectrum extends infinitely in both directions. There are radio waves kilometers long and gamma rays smaller than atoms, and we are blind to all of it without technology. We hear a small range of sound frequencies from about 20 Hz to 20,000 Hz. But elephants communicate at infrasound frequencies we cannot hear, and bats navigate using ultrasound beyond our perception. We experience time flowing in one direction at a steady pace. But physics reveals that time can slow down or speed up depending on velocity and gravity. We experience space as three-dimensional and Euclidean, with parallel lines staying parallel. But general relativity shows us that space can curve and warp, that parallel lines can converge or diverge, that the geometry of the universe is far stranger than our intuitions suggest. The universe we experience is not the universe as it truly is. It is a simplified, edited version that our brains construct from limited sensory data, filtered through our evolutionary history and neurological architecture. In the infrared spectrum, the story of the galactic center became crystal clear. Stars danced around an invisible force. Heat glowed where the eye saw nothing. And the shape of the galaxy's hidden center began to emerge, revealing a supermassive black hole with the mass of about 4 million suns, about 8.54 times 10 to the power of 36 kilograms, packed into a space smaller than our solar system. This discovery would not have been possible without the patient work of two teams of astronomers who spent years, decades even, tracking the movements of individual stars near the galactic center. One team was led by Reinhard Genzel, working out of the Max Planck Institute in Germany. Another was led by Andrea Ghez at the University of California, Los Angeles. Their work, which earned them the Nobel Prize in Physics in 2020, exemplifies the nature of modern science. They did not make their discovery in a flash of insight or a single dramatic observation. They made it through years of painstaking data collection, careful analysis, and incremental refinement of their techniques. Science at the frontier is not about sudden revelations or eureka moments. It is about patience, precision, perseverance, and the slow accumulation of evidence over years and decades. Each team used powerful ground-based telescopes fitted with advanced imaging systems to peer through the thick dust of the galactic center. Even with infrared telescopes, the challenge was immense. Earth's atmosphere creates constant interference, blurring images and making stars appear to shimmer or move randomly. Light passing through the atmosphere is distorted by turbulence, temperature variations, and density fluctuations. This is why stars twinkle, and why ground-based astronomy has historically been limited in resolution. To deal with this, astronomers used a technology called adaptive optics, which allowed the telescopes to adjust in real time, cancelling out much of the distortion caused by the air above. Adaptive optics works by measuring the distortion of light from a bright reference star, and then using a deformable mirror to create an equal and opposite distortion, effectively cancelling out the atmospheric turbulence. The mirror can adjust its shape hundreds or even thousands of times per second, following the rapid changes in the atmosphere. This technology has revolutionized ground-based astronomy, allowing telescopes on Earth to achieve resolutions approaching those of space telescopes. Near the region known as Sagittarius A*, they found stars moving at incredible speeds, whipping around a point in space like comets flying past a campfire. Some traveled at over 5,000 kilometers per second, fast enough to go from Earth to the Moon in just over a minute. But it was not the speed alone that mattered. It was the orbital mechanics, the precise mathematical relationship between velocity, distance, and the mass of whatever they were orbiting. These relationships are described by Kepler's laws of planetary motion and Newton's law of universal gravitation, laws that have been tested and confirmed countless times throughout the solar system and beyond. The key breakthrough came from watching these stars over time, measuring their positions year after year with extraordinary precision, building up a complete picture of their orbits. One star in particular, known as S2 or sometimes S02, stood out. It was a bright star moving in a tight, fast orbit that brought it incredibly close to the invisible object at the center, approaching to within just 17 light hours, about 120 astronomical units, closer than 3 times the distance from the Sun to Pluto. By measuring S2's orbit precisely, astronomers could calculate the mass of the object it was orbiting using Kepler's third law, which relates orbital period to orbital radius and central mass. The result was stunning and unambiguous. The object had the mass of about 4 million suns, but it was packed into a space smaller than our solar system. It did not emit light like a star. It did not show any signs of being a cluster of smaller objects. There was only one thing it could be: a supermassive black hole. But here is what makes this discovery philosophically profound. The black hole at the center of our galaxy cannot be observed directly. It emits no light of its own. We cannot see it, photograph it in the conventional sense, or detect it with any direct means. We know it exists only through its gravitational influence on visible objects around it. We infer an invisible reality from its effects on what we can see. This is the same method by which we detect dark matter, dark energy, and the cosmic event horizon itself. Modern cosmology is largely the science of the invisible, of deducing the existence of things we cannot observe from subtle patterns in the things we can. This should make us pause and reflect on the nature of knowledge and reality. How much of what we consider real is actually invisible to us? How much of reality consists of things we can only infer, never observe directly? And how reliable are those inferences? We believe in atoms and molecules, in electrons and quarks, in fields and forces, not because we have seen them with our eyes, but because the patterns they predict match the patterns we observe. We build up a picture of reality from indirect evidence, from shadows and echoes and mathematical relationships. The black hole at the center of our galaxy has a Schwarzschild radius, the size of its event horizon, of roughly 12 million kilometers, or about 7.4 million miles. That sounds huge, and in human terms it is. But in cosmic terms it is surprisingly small. It is just over 17 times the diameter of the Sun, all packed into an invisible sphere at the heart of the Milky Way. Everything inside that sphere is cut off from the rest of the universe. The black hole itself is not a physical ball or object in the traditional sense. The event horizon is not a solid surface you could touch or land on. It is simply the threshold where space and time bend so steeply inward that no outward path exists, where escape velocity exceeds the speed of light. The term Schwarzschild radius comes from the German physicist Karl Schwarzschild, who in 1916 was the first to find a mathematical solution to Einstein's new theory of general relativity that described such an object. His equations told us that if you compress enough mass into a small enough space, the pull of gravity becomes absolute at a certain radius. That radius depends only on the object's mass. For any given mass, you can calculate the Schwarzschild radius using a simple formula: 2 times the gravitational constant times the mass divided by the speed of light squared. And for black holes, it is all that is left to define their size. Mass and angular momentum and electric charge, that is all a black hole has. Everything else, all other information about what fell in, is lost. This is sometimes called the no-hair theorem. Black holes have no hair, no distinguishing features beyond those 3 quantities. From far away, the Schwarzschild radius is a purely mathematical line, an abstract concept with profound physical consequences. You could orbit near it, circle around it, even hover just outside it, if you had some impossible way to counteract gravity, perhaps with a rocket providing continuous thrust. But get closer, and the landscape changes dramatically. Space itself is falling inward, pulled faster and faster as it approaches the event horizon. The closer you are, the more extreme time dilation becomes. From your perspective, everything would seem normal. Your watch would tick normally. Your heart would beat normally. But from the outside universe's perspective, you would appear to slow down, your movements becoming more and more sluggish, your light shifting to red as photons lose energy climbing out of the gravitational well, fading and eventually disappearing entirely before you ever seem to cross the line. This is one of the strangest predictions of general relativity. Someone falling into a black hole would never be seen to cross the event horizon from an outside observer's perspective. They would seem to freeze at the horizon, becoming dimmer and redder and more stretched out, asymptotically approaching the event horizon, but never quite reaching it. Meanwhile, from the falling person's perspective, they would cross the horizon in finite time, experiencing nothing special at the moment of crossing, then inevitably falling toward the singularity at the center. The Event Horizon Telescope collaboration achieved something remarkable in recent years. They created an image of the shadow of the supermassive black hole at the center of the galaxy M87, and later, an image of Sagittarius, a star itself. These images show a glowing ring of radio light around a dark center. That dark center is not the black hole itself, but its shadow, a slightly larger silhouette caused by light being bent and swallowed near the event horizon. The actual Schwarzschild radius lies just inside that shadow's edge. Because Sagittarius, a star, is so far away, about 26,000 light-years, the whole thing appears smaller in the sky than a donut on the moon would look to someone standing on Earth. That is why imaging it took years of coordination, enormous computing power, and the precision of atomic clocks. The Event Horizon Telescope is not a single telescope, but a network of radio telescopes spread across the entire Earth, working together as one giant telescope the size of our planet. By combining observations from telescopes in Chile, Hawaii, Arizona, Spain, and Antarctica, astronomers created a virtual telescope with unprecedented resolution. The technical challenges were immense. The telescopes had to observe simultaneously, coordinating their observations to within nanoseconds using atomic clocks. They recorded petabytes of data, so much that it could not be transmitted over the internet, and had to be physically shipped on hard drives. Then, teams of scientists spent years correlating the data, processing it, and extracting an image from the interference patterns. The result was a historic photograph, the first direct visual evidence of an event horizon, proof that these exotic objects, predicted by general relativity, actually exist. Beyond the Schwarzschild radius lies the region we cannot observe directly. According to general relativity, once you pass the event horizon, you are inevitably drawn toward the singularity at the center. The singularity is predicted to be a point of infinite density, where the known laws of physics break down completely. We do not know what really happens there. Some theories suggest it might be a tiny, infinitely curved region of spacetime, a place where curvature becomes infinite, and our equations produce meaningless infinities. Others propose that quantum effects, which general relativity does not account for, could smear it out or replace it entirely with something new, perhaps a Planck star or a bridge to another universe through a wormhole. But as far as our instruments are concerned, and as far as the outside universe is concerned, the singularity is forever hidden behind the event horizon. The Schwarzschild radius is not just a limit for light. It is a limit for cause and effect, for information itself. No signal from inside can ever influence the outside. That means the inner workings of a black hole are cut off from the rest of the cosmos in a very fundamental way. This is why so much of black hole science has to be done indirectly. We measure the orbits of nearby stars, watch how hot gas behaves, or detect the flickers of light caused by magnetic or gravitational turbulence just outside the event horizon. This raises a fascinating philosophical question. If a black hole is surrounded by an event horizon beyond which nothing can escape, including light and information, is there any meaningful sense in which the interior of the black hole exists? The information about what has fallen into a black hole seems to be lost forever, perhaps even destroyed, which would violate quantum mechanics according to some interpretations. This is called the black hole information paradox, and it has troubled physicists for decades. Stephen Hawking famously proposed that black holes are not entirely black. They emit radiation through a quantum process, now called Hawking radiation. Virtual particle pairs are constantly appearing and disappearing throughout empty space due to quantum fluctuations. Near the event horizon of a black hole, one particle of a pair might fall in while the other escapes. From an outside perspective, this looks like the black hole is emitting radiation. This radiation carries away energy, causing the black hole to slowly lose mass and eventually evaporate completely. But this creates a paradox. If information that falls into a black hole is destroyed, this violates a fundamental principle of quantum mechanics, which says that information can never be truly destroyed, only transformed. The paradox has led to decades of debate and has driven the development of new theories attempting to reconcile quantum mechanics and general relativity. Some propose that information is encoded on the event horizon itself, in subtle correlations in the Hawking radiation. Others suggest that the interior and exterior of a black hole are connected in ways we do not yet understand, perhaps through higher dimensions or quantum entanglement. Similarly, if galaxies have crossed our cosmic event horizon and can never again send us information, in what sense do they still exist for us? They may continue to exist in some absolute sense, obeying the laws of physics and evolving over time. But they no longer exist in our observable universe. They have passed beyond the veil of knowability. Philosophically, this is similar to asking whether the past exists. Yesterday is gone and can never be revisited or changed. It exists only as patterns of memory and records in the present. Does it still exist somewhere, somehow, or has it ceased to be, except as information encoded in the present? These questions touch on the deepest problems in philosophy: the nature of time, the reality of the past and future, the relationship between knowledge and existence. Different philosophical traditions give different answers. Eternalism, sometimes called the block universe view, holds that past, present, and future all exist equally. The passage of time is an illusion created by our consciousness moving through a static, four-dimensional spacetime. Presentism holds that only the present moment exists. The past no longer exists, and the future does not yet exist. Growing block theories suggest that the past and present exist, but the future does not. Each view has profound implications for free will, causation, and the nature of reality itself. These discoveries about what lies at the center of our galaxy and at the edge of the observable universe connect in fascinating ways. Both involve understanding how gravity shapes the cosmos on the largest and smallest scales. Black holes represent regions where space-time is curved so intensely that not even light can escape. The edge of the observable universe represents a different kind of boundary, one created by the expansion of space itself rather than by gravity. Yet both teach us about the fundamental limits of what we can know and observe. Both create event horizons beyond which information cannot pass. Both cut off regions of space-time from our ability to investigate them. When we look toward the edge of the observable universe, we are not just looking across space. We are looking back in time. Light travels at a finite speed, about 300,000 kilometers per second. So when we observe distant galaxies, we see them as they were when that light began its journey. The most distant galaxies we can see appear as they were more than 13 billion years ago, when the universe was young and stars were just beginning to form, when the first generation of galaxies was coalescing from primordial clouds of hydrogen and helium. In a very real sense, powerful telescopes are time machines, allowing us to witness the history of the cosmos unfold before our eyes. We can see galaxies at different stages of evolution, from young, irregular galaxies full of hot blue stars, to mature spiral galaxies like our own, to old elliptical galaxies where star formation has largely ceased. We can watch the universe grow and change, see structure emerge from chaos, complexity from simplicity. This is one of the most remarkable achievements of modern astronomy. We can literally see the past, observe history directly, rather than inferring it from present evidence. But this raises another profound question. If we can see the past by looking at distant objects, why can we not see the future? The answer lies in the structure of space-time and the nature of causality. Information can only travel at the speed of light or slower. Therefore, We can only see events from our past light cone, the region of spacetime from which light has had time to reach us. The future light cone, the region of spacetime that we could influence with signals sent now, is ahead of us and unknowable. This asymmetry in time, the fact that we remember the past but not the future, that causes always precede effects, is related to the second law of thermodynamics and the increase of entropy. This time delay creates an interesting perspective on cosmic exploration and the nature of existence at relativistic speeds. If someone could somehow travel at speeds approaching the speed of light, something fascinating happens due to an effect called time dilation. From the perspective of the traveler, time actually slows down relative to the rest of the universe. This is not an illusion or a trick of perception. It is a real physical effect predicted by Einstein's theory of special relativity and confirmed by countless experiments. Time dilation has been tested and verified in numerous ways. GPS satellites orbiting Earth have to account for this effect, or their clocks would run faster than clocks on Earth's surface, and GPS would accumulate errors of about 10 kilometers per day. Atomic clocks flown on airplanes run slower than identical clocks left on the ground, exactly as predicted by relativity. Unstable particles called muons, created in the upper atmosphere by cosmic rays, should decay before reaching the ground, based on their known lifetime, 2.01 seconds. But we detect them at ground level because time dilation extends their lifespan from our perspective. Time dilation means that while traveling at near light speed, you would experience less time passing than observers who remained stationary. Your heartbeat would seem normal to you. Your thoughts would proceed at their usual pace. Your watch would tick away seconds at its normal rate. But relative to someone watching from Earth, your entire existence would be moving in slow motion. If you could look back at Earth, you would see time speeding up, days and nights flickering past like a strobe light, seasons changing in moments, years passing in seconds, civilizations rising and falling before your eyes, like flowers blooming and wilting in a time-lapse video. The mathematics of time dilation is given by the Lorentz factor, which depends on velocity. At 10% light speed, time dilation is barely noticeable, just about 1% slower. At 50% light speed, your clock would run about 87% as fast as Earth clocks, a noticeable but not dramatic difference. But at 90% light speed, your clock would run at less than half the speed of Earth clocks. And at 99.9% light speed, your clock would tick 44 times slower than those on Earth. In principle, if you could maintain constant acceleration at 1 gravity, the comfortable force we experience every day on Earth, standing on the surface, for about 20 years of ship time, you could reach the edge of the observable universe, some 46 billion light-years away. Of course, Earth would experience billions of years passing during your journey. Everyone you ever knew would be dead. Their children would be dead. Their civilization would likely be dust. The continents would have shifted position. The stars would have moved to different locations in the sky. The sun would be older, larger, redder. You would return, if you returned at all, to a world utterly transformed, to a time so far removed from your departure that nothing would be recognizable. Not the geography, not the politics, not the culture, not even the position of the stars. This creates a profound asymmetry in the universe. While civilizations remain isolated from each other by the cosmic speed limit, trapped in their own corners of spacetime, individual explorers could potentially visit multiple civilizations within their own lifetimes, at least from their own reference frame. You could be a cosmic messenger carrying news and knowledge between worlds that could never communicate directly with each other. You could witness the rise and fall of multiple civilizations, see different evolutionary paths, different solutions to the problem of existence. But you would be a messenger without a home, a traveler without the possibility of return, because home would cease to exist in any meaningful sense during your journey. Imagine the psychological weight of such a journey. You would be volunteering to sever all connections with everyone and everything you have ever known. You would be choosing to become unstuck in time, to leap forward through the centuries and millennia while experiencing only years. You would witness the birth and death of stars, the collision of galaxies, the evolution of cosmic structure on scales that normally require billions of years. But you would do so alone, or at most with a small crew of fellow travelers who share your exile from normal time. Some might call this immortality. After all, you could travel indefinitely into the future, experiencing a normal lifespan subjectively while the universe ages around you. You could outlive stars, outlive galaxies, outlive civilizations. But it is a strange kind of immortality, one that cuts you off from any continuous thread of culture, history, or relationship. You would be immortal but utterly alone, a ghost haunting the distant future, carrying memories of a past so remote it might as well be mythological, speaking a language no one else remembers, remembering a world no one else has even heard of. This brings us to one of the most visually spectacular and philosophically significant effects of relativistic travel, the aberration of light. As you accelerate toward light speed, the universe itself begins to look different, transforming in ways that challenge our basic intuitions about space and perception. You might expect to see stars whizzing past, like in science fiction movies, like watching scenery rush by the window of a speeding train. But that is not what happens at all. Instead, something far stranger, far more alien occurs. Due to an effect called relativistic aberration, the stars appear to shift position in the sky. Stars that were behind you seem to move to the sides and then toward the front. As you approach light speed, more and more of the universe appears to compress into a bright circle directly ahead of you, as if the entire cosmos is collapsing into a single point. Meanwhile, the region behind you becomes increasingly dark and empty. This is not an optical illusion or a trick of the light. It is a real consequence of how light behaves at relativistic speeds, a genuine transformation of your observable universe. The universe you observe is genuinely different from the universe observed by someone at rest. This raises a profound question about the nature of reality itself. If different observers see genuinely different universes, depending on their relative motion, which one is real? Is there an objective universe independent of all observers? Or is reality fundamentally perspectival, different for each observer, depending on their motion and position in space-time? Einstein's theory of relativity suggests the latter. There is no privileged frame of reference, no absolute perspective from which the universe can be viewed as it truly is. Every observer sees a valid slice of reality, and physics provides the rules for translating between different perspectives. The universe is not a fixed stage on which events occur. It is a dynamic tapestry of space-time that looks different depending on where and how you observe it. Space and time themselves are relative, depending on the observer's motion. At 50% light speed, the aberration effect is noticeable, but not extreme. The stars ahead of you brighten slightly, and those behind dim. At 90% light speed, you would see about half the sky compressed into a 60-degree cone in front of you. The stars behind you would appear dimmer and shifted toward the red end of the spectrum, while stars ahead would be brighter and shifted toward blue. At 99.9% light speed, almost the entire visible universe would be compressed into a blindingly bright disk just 25 degrees wide, directly ahead. Behind you would be darkness, almost total blackness, as if you were fleeing from existence itself into an increasingly narrow tunnel of light. The visual effects go even deeper than this simple positional aberration. The Doppler effect, which you might know from the way ambulance sirens change pitch as they pass by, becomes extreme at relativistic speeds. Just as sound waves are compressed when a source approaches you and stretched when it recedes, light waves undergo the same transformation. Light from stars ahead of you gets compressed to shorter wavelengths, blue shifted, while light from behind is stretched to longer wavelengths, red shifted. At extreme speeds, this shift is so dramatic that visible light from stars ahead would shift into the ultraviolet, X-ray, and even gamma-ray range. These are forms of electromagnetic radiation with wavelengths much shorter than visible light, invisible to the human eye but potentially lethal to living tissue. Stars behind you would shift into the infrared and radio waves, wavelengths longer than visible light. You would need special sensors and detectors to see anything at all, because the familiar visible light spectrum would come only from stars to your sides, and even that would be distorted and shifted. But think about what this means for your experience of the universe. The cosmos you observe would be genuinely different from the cosmos observed by someone at rest. You would be bathed in high-energy radiation from ahead, potentially lethal doses of X-rays and gamma rays that would require heavy shielding to survive. Meanwhile, the stars behind you would fade to invisibility in the infrared. The universe would appear hostile, aggressive, as if punishing you for your audacity in challenging the cosmic speed limit, as if the cosmos itself resists your attempt to approach light speed. At 99.9% light speed, a signal you transmit at normal radio frequencies might be received on Earth as infrared radiation or even visible light, depending on your speed and direction. If you are approaching Earth, your radio signals would be blue shifted by a factor of about 22. A signal you transmit at 100 MHz would be received at about 2.2 GHz. If you are moving away from Earth, the same signal would be red shifted down to about 4.5 MHz. Earth would need to know exactly when to listen and at what frequency to receive your transmissions. But the frequency shift is just the beginning of the communication problem. The relativistic Doppler effect also affects the rate at which information is transmitted. If you are moving away from Earth at high speed, your signals arrive stretched out in time. A 1-hour message you transmit might take 22 hours to play back on Earth at normal speed. Conversely, if you are approaching Earth, your signals would arrive compressed in time. A 1-hour message would play back in less than 3 minutes. This creates a bizarre situation where the very act of communication becomes distorted by your motion. Your voice would sound like a slow, deep rumble if you are moving away, or like a high-pitched squeak if you are approaching. Digital data would need to be carefully processed to account for these time distortions. Even if you send a message to Proxima Centauri, our nearest stellar neighbor, at 4.24 light-years away, and Earth immediately sent a reply, you would not receive their response for 8.48 years, measured in Earth time. But here is where it gets worse. Due to time dilation, those 8.48 years of Earth time might correspond to only a few months of your time, depending on your velocity. So from your perspective, you send a message and get a reply in a few months. But that reply is describing an Earth that is nearly a decade older than when you left. Everyone you knew has aged 8.5 years, in what feels like a few months to you. Even if we solve the technical problems of relativistic communication, there is a deeper issue. the psychological impact of the communication delays. Imagine trying to maintain relationships with people on Earth when every conversation takes years to complete. You send a message asking how someone is doing. Years later, you receive a reply telling you about events that happened years ago from their perspective. By the time you receive their message, their situation might have changed completely. They might have married, had children, moved to another city, changed careers. Or they might have died. And you would not know until the light carrying that information finally reaches you. This is the fundamental isolation imposed by the cosmic speed limit. It cuts not just across space, but across time. It makes real-time communication impossible beyond local distances. It forces anyone who travels at relativistic speeds to accept a fundamental loneliness, a disconnection from the normal flow of human time and relationship. You would be living in your own timeline, separate from everyone else, able to communicate only in delayed bursts that carry news of a past that is already gone. These effects remind us that our everyday experience of reality is just one slice of a much stranger and more complex universe. The laws of physics remain the same everywhere, but the experience of those laws changes dramatically depending on your velocity and your reference frame. A meter stick moving at 99% light speed contracts to about 1/7 of its rest length from the perspective of a stationary observer. But to someone moving with the meter stick, it appears perfectly normal. Time, space, simultaneity, mass, energy, all of these seemingly absolute features of reality turn out to be relative, dependent on perspective. This consistency of physical laws across all reference frames is called Lorentz invariance, named after the Dutch physicist Hendrik Lorentz, who first derived the transformation equations. Despite extensive searches spanning decades, scientists have found no violations of it. Experiments ranging from tabletop laser systems to observations of gamma rays from distant galaxies all confirm that physical laws remain exactly the same, regardless of motion. The speed of light is the same for all observers, regardless of their velocity. This constancy of the speed of light is the foundation of special relativity and leads to all the strange effects we have been discussing. You might wonder why the speed of light is constant. Why does light always travel at 300,000 kilometers per second, regardless of the motion of the source or observer? The answer lies deep in the structure of spacetime itself. Light is an electromagnetic wave, and the speed of electromagnetic waves is determined by the electrical and magnetic properties of space itself. If the speed of light could vary, it would mean the fundamental properties of space are changing, which would violate basic principles of physics. The relationship between entropy and information provides yet another fascinating aspect of the cosmic speed limit and our ability to understand the universe. According to the second law of thermodynamics, entropy always increases in isolated systems. Entropy is a measure of disorder, of randomness, of the number of possible microscopic states that correspond to a given macroscopic state. A broken egg has higher entropy than an intact egg. A mixed cup of coffee has higher entropy than coffee and cream separated. Heat flowing from hot to cold increases entropy. This is one of the few laws of physics with a preferred direction in time. Most physical laws work equally well whether time runs forward or backward. The equations of motion, the laws of electromagnetism, even quantum mechanics to some extent, are time reversible. You can reverse the equations and they still make sense, still describe valid physical processes. But entropy gives time an arrow. It distinguishes past from future. The past is lower entropy, more ordered, more organized. The future is higher entropy, more disordered, more random. A video of an egg unbreaking itself and jumping back into its shell would immediately look wrong because it shows entropy decreasing, time running backward. But information theory tells us that information and entropy are fundamentally related. This connection was first recognized by physicist James Clerk Maxwell and later formalized by Claude Shannon and others. Information is a measure of order, of pattern, of distinguishability. The more information something contains, the lower its entropy. A highly ordered crystal has high information content and low entropy. A cloud of random gas has low information content and high entropy. Information and entropy are two sides of the same coin, two ways of describing the same underlying reality. Erasing information increases entropy. This is not just a theoretical result. It has been proven mathematically and demonstrated experimentally. When you delete a file from a computer, the computer must dissipate heat, increasing the entropy of its environment, because erasing information is equivalent to increasing entropy. Preserving information fights against entropy. Living organisms maintain low entropy internally by processing information and exporting entropy to their environment. We are, in a very real sense, information processing systems, fighting a constant battle against the second law of thermodynamics. In a deep sense, the growth of entropy is the destruction of information, the loss of pattern and structure, as systems evolve toward equilibrium, toward maximum entropy, toward what is called the heat death of the universe. If the universe continues expanding and entropy continues increasing, eventually all energy will be evenly distributed, all temperature differences will disappear, and no further work or information processing will be possible. This is the ultimate fate of an expanding universe. Not a violent end, but a quiet fading, a slow dissolution of all structure and pattern and information into uniform maximum entropy. As objects approach light speed, the information required to describe their quantum states approaches infinity. Every particle has a position, a momentum, a spin, and many other quantum properties. To describe a moving object completely, you need to know all of these properties for all of its particles. But as the object moves faster, relativistic effects make its description more complex. Its energy increases without bound as you approach light speed. Its momentum increases without bound. The number of possible quantum states seems to explode toward infinity. The universe might prevent light speed travel simply to avoid infinite information density, which would violate thermodynamic principles. This is a profound thought worth contemplating. The cosmic speed limit might not be an arbitrary rule imposed from outside, not a limitation of technology or engineering, but an inevitable consequence of the relationship between information, entropy, and the structure of spacetime itself. The universe cannot allow infinite information density, because that would require zero entropy, perfect order, complete distinguishability of all states. But the second law demands that entropy increase. The cosmic speed limit might be the universe's way of enforcing thermodynamic consistency, of preventing violations of its own fundamental laws. Consider the practical impossibility from an engineering standpoint. The International Space Station, humanity's most ambitious space construction project to date, orbits at about 7.66 kilometers per second, just 0.0025% of light speed. It took dozens of launches, hundreds of billions of dollars, and decades of international cooperation to achieve this. The ISS masses about 420,000 kilograms and required over 40 assembly flights to construct. To reach even 1% of light speed would require energy and engineering capabilities roughly 400,000 times greater. The gap between our current abilities and light speed is not just large. It is astronomical, perhaps fundamentally unsurmountable. The kinetic energy of an object is given by 1/2 mass times velocity squared in classical physics. But at relativistic speeds, this formula breaks down. The relativistic kinetic energy is given by the mass times the speed of light squared, times the quantity gamma-1, where gamma is the Lorentz factor. As velocity approaches the speed of light, gamma approaches infinity, and so does the kinetic energy. To accelerate any object with mass to the speed of light would require infinite energy. Let us put some numbers to this. To accelerate a modest spacecraft of 1,000 kilograms to 99% light speed would require about 6 × 10 to the power of 20 joules of energy, equivalent to the total energy output of the Sun for about 50 seconds. To reach 99.9% light speed would require about 10 times more energy than that. And to actually reach 100% light speed would require literally infinite energy, which is why it is impossible for anything with mass to reach or exceed light speed. But the energy problem is just the beginning. Even if we somehow solved the energy problem, perhaps through some undiscovered physics or technology, there would be other barriers. At relativistic speeds, even the thin interstellar medium becomes a significant hazard. Space between stars is not truly empty. It contains on average about 1 hydrogen atom per cubic centimeter, along with trace amounts of other elements, cosmic rays and photons. At everyday speeds, this is negligible, but at 99% light speed, each collision with one of these particles would release energy comparable to a particle accelerator collision. The Parker Solar Probe, currently our fastest spacecraft, travels at about 0.06% light speed at its maximum velocity as it approaches the Sun. Even at this relatively slow speed, it requires a thick heat shield to protect it from solar radiation and particles. At true relativistic speeds, collisions with interstellar hydrogen would be so energetic that they would create showers of secondary particles, including pions, muons, and other exotic particles. The spacecraft would be flying through a constant storm of cosmic rays, requiring shielding so thick and massive that it might be impractical to accelerate it to relativistic speeds in the first place. NASA's Voyager probes, traveling at a mere 0.006% light speed, have given us valuable data about the interstellar medium. They have shown that space between stars is more complex than we thought, with magnetic fields, varying densities of particles, and regions of compressed plasma. All of these would become serious hazards at relativistic speeds. The interstellar medium would essentially become a particle radiation beam bombarding the spacecraft from ahead. Consider what this means for biological organisms. Our bodies evolved in Earth's gentle gravitational field with its leisurely pace through spacetime. At relativistic speeds, every cell in your body would experience stresses that evolution never prepared us for. The calcium in your bones, the iron in your blood, the very DNA that makes you who you are, all would be subject to forces that could tear apart molecular bonds. Consider the effect on your cardiovascular system. Your heart pumps blood based on pressure differentials that assume normal physics. At relativistic speeds, the altered mass due to relativistic effects and time dilation would affect blood flow in unpredictable ways. Would your blood become more massive? Would chemical reactions in your cells slow down or speed up relative to the outside universe? We simply do not know, because no living organism has ever experienced these conditions. But computer simulations suggest the results would be catastrophic. There is also the psychological aspect to consider. Imagine knowing that while you experience a journey of months, everyone you have ever known on Earth ages decades or centuries. This is not science fiction. It is the real consequence of time dilation. The emotional and mental toll of such temporal isolation would be unprecedented in human experience. You would return from your journey, if you returned at all, to find the world transformed beyond recognition. Your loved ones aged or gone. Your culture changed in ways you could never have predicted. Your language evolved to the point of incomprehensibility. You would be a stranger in a strange land, a refugee from the past, washed up on the shores of the future. Let me share something that really drives home the impossibility, the energy density problem. As you pump more energy into accelerating an object, that energy doesn't just disappear. It adds to the object's relativistic mass. At speeds approaching light speed, you would need to concentrate so much energy in one place that you would risk creating a black hole. Yes, you heard that right. Trying to reach light speed could theoretically collapse your spacecraft into a singularity, creating a black hole that would swallow both the spacecraft and anything nearby. The Schwarzschild radius, the size of a black hole's event horizon, is given by 2 times the gravitational constant times the mass divided by the speed of light squared. For normal masses, this radius is tiny. For the Earth, the Schwarzschild radius is about 9 millimeters. The Earth would have to be compressed to less than 2 centimeters in diameter to become a black hole. But as you add energy to accelerate an object, that energy becomes mass through Einstein's famous equation, E equals mc squared. At some point, the mass-energy density could become so high that it collapses into a black hole, defeating the entire purpose of the journey. The vacuum of space itself presents unexpected challenges at high speeds. Quantum field theory tells us that empty space is not really empty. It is filled with virtual particles constantly popping into existence and annihilating, borrowing energy from the vacuum for brief moments allowed by Heisenberg's uncertainty principle. At normal speeds, these quantum fluctuations are irrelevant, undetectable background noise. But at relativistic speeds, something called the Unruh effect predicts that you would perceive these fluctuations as real radiation. The Unruh effect says that an accelerating observer sees a thermal bath of particles, where an inertial observer sees empty space. The faster you accelerate, the hotter this quantum bath would appear, eventually becoming lethal radiation that emerges from the nothingness of the vacuum itself. This is one of the strangest predictions of quantum field theory in curved spacetime. And while it has not been directly observed, due to the tiny effect at achievable accelerations, most physicists believe it is real. Scientists have discovered another bizarre effect called relativistic beaming. As objects approach light speed, the radiation they emit becomes concentrated in a narrow cone in their direction of travel. This means a spacecraft's headlights would become a deadly beam of concentrated energy, while its engines would be nearly invisible from behind. Communication would become impossible as radio waves undergo the same beaming effect. Everything emitted from the spacecraft would be compressed into a narrow forward cone, making it invisible to observers anywhere except directly ahead. The discovery of dark matter's gravitational effects adds yet another layer of complexity to any hypothetical journey through space, and to our understanding of what the universe is made of. Dark matter, which outweighs normal matter 5 to 1, creates invisible gravitational fields throughout space. Any spacecraft approaching light speed would have to navigate through these invisible gravitational wells and currents. It would be like trying to sail through an ocean where most of the waves and currents are invisible, constantly pulling you off course with forces you cannot see or predict, changing your trajectory in ways you cannot anticipate. But dark matter affects not just space travel, but our entire understanding of cosmic structure and evolution. Without dark matter, galaxies would fly apart. The stars in galactic disks are moving so fast that normal matter alone could not hold them together. There is not enough visible matter to provide the gravitational glue. Astronomers first noticed this problem in the 1970s, when Vera Rubin and others measured the rotation curves of galaxies. They found that stars in the outer regions of galaxies were moving just as fast as stars near the center, when they should have been moving much slower if only visible matter was present. This implied the existence of vast halos of invisible matter surrounding galaxies, providing the extra gravity needed to hold them together. Since then, evidence for dark matter has accumulated from many independent sources: gravitational lensing, galaxy cluster dynamics, the cosmic microwave background, large-scale structure formation. All point to the same conclusion. Most of the matter in the universe is dark, invisible, detectable only through gravity. Yet we do not know what dark matter is made of. It is not made of atoms like ordinary matter. It is not made of protons, neutrons, or electrons. It does not interact with light at all, which is why it is invisible. It seems to interact only through gravity, and possibly through some other extremely weak force. Detecting it directly has proven extraordinarily difficult, despite decades of trying. Underground laboratories around the world house detectors designed to catch the rare interaction of a dark matter particle with ordinary matter. These experiments are typically located deep underground to shield them from cosmic rays and other background radiation. They use extremely sensitive detectors cooled to near absolute zero, looking for the tiny energy deposit that would indicate a dark matter particle collision. So far, these experiments have not found definitive evidence, but they continue to push the boundaries of sensitivity, ruling out more and more of the parameter space where dark matter particles might exist. Other experiments search for dark matter indirectly. They look for the products of dark matter particles, annihilating each other in regions of high dark matter density, such as the center of the galaxy or the sun. These searches scan the sky for unusual patterns of gamma rays, neutrinos, or other radiation that might signal dark matter's presence. Again, so far no definitive detection, but the search continues. The fact that most of the matter in the universe is invisible to us, detectable only through its gravitational effects, is profoundly humbling. We have built our entire civilization using atoms, baryonic matter, the same atoms that make up stars and planets and all visible matter. But atoms are a minority component of the cosmos. The universe is made mostly of stuff we cannot see, touch, or directly detect. We are embedded in a reality we barely understand, surrounded by an invisible ocean of dark matter, and bathed in the even more mysterious dark energy that drives the accelerating expansion. Dark energy makes up about 68% of the universe's total mass and energy content. Unlike matter, which attracts through gravity, dark energy seems to have a repulsive effect, pushing space apart and causing the expansion to accelerate. We have no idea what it is. The simplest explanation is that it is a cosmological constant, a property of space itself, an energy density inherent in the vacuum. Einstein originally introduced the cosmological constant to make his equations allow for a static universe, then called it his biggest blunder when Edwin Hubble discovered the universe is expanding. But observations of distant supernovae in the late 1990s showed that the expansion is accelerating, and the cosmological constant was resurrected as the simplest explanation for dark energy. But we do not really understand it. Why does the vacuum have this energy density? Why does it have the particular value it does, which seems incredibly finely tuned? If you calculate the vacuum energy density from quantum field theory, you get a value that is 10 to the power of 120 times larger than what we observe, one of the worst predictions in the history of physics. This is called the cosmological constant problem, and it remains one of the deepest unsolved mysteries in theoretical physics. Alternatively, dark energy might not be constant. It might be a dynamic field that varies over time, sometimes called quintessence. Or it might be a sign that our theory of gravity breaks down on cosmic scales, requiring modifications to general relativity. We do not know, and we have very few clues about how to find out. This is frontier physics at its most uncertain and exciting. This means that everything we can see and touch and measure directly, all the atoms in all the stars and planets and living things, all the matter we have studied in all our laboratories and accelerators, makes up less than 5% of the universe. 95% of the universe consists of things we do not understand. Dark matter and dark energy, invisible and mysterious, known only through their effects on the tiny sliver of the cosmos we can directly observe. We are, in a very real sense, living in a universe we barely comprehend, made mostly of substances we cannot see or touch. Yet through careful observation, clever experiments, and mathematical reasoning, we can infer the existence of these hidden components and study their effects on the visible universe. The cosmic web that dark matter forms provides the scaffolding on which galaxies grow and the large-scale structure of the universe develops. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny density fluctuations. Quantum ripples inflated to cosmic scales during the inflationary epoch. But those tiny fluctuations, just one part in 100,000 variations in density, grew over time under the influence of gravity. Regions that were slightly denser attracted more matter, becoming denser still. This is called gravitational instability, a positive feedback process where dense regions get denser. Over millions of years, this process created a web-like structure, with dense filaments of matter separated by vast empty voids. This cosmic web is one of the largest structures in the universe, spanning billions of light years, yet it is made mostly of invisible dark matter. Visible matter, the atoms that make up stars and planets and us, followed the gravitational potential wells created by dark matter. Gas clouds fell into the densest regions, were compressed by gravity, heated up due to gravitational potential energy being converted to thermal energy, and ignited as stars when the temperature and pressure became high enough for nuclear fusion to begin. These stars grouped together into galaxies, and galaxies clustered along the dark matter filaments like beads on a string. The result is the cosmic web we observe today, a pattern that spans billions of light years and contains billions of galaxies, yet which is made mostly of invisible dark matter. From far away, the universe looks like foam or sponge, with galaxies concentrated on the surfaces of enormous bubbles, surrounding vast voids containing almost nothing. This structure emerged naturally from gravity, acting on the tiny initial density fluctuations, a simple process producing complexity and beauty on the grandest scales imaginable. Observations of galaxy clusters, where hundreds or thousands of galaxies are bound together by gravity, reveal the presence of dark matter through a technique called gravitational lensing. Just as a glass lens bends light through refraction, the gravity of massive objects bends the path of light, traveling near them through the curvature of spacetime. Einstein predicted this effect as a consequence of general relativity, and it was one of the first confirmations of his theory. During a solar eclipse in 1919, Arthur Eddington observed that stars near the Sun appeared shifted from their true positions, exactly as Einstein predicted. When we look at distant galaxy clusters, we see distorted images of even more distant galaxies behind them, stretched into arcs and rings and multiple images by the gravitational field of the intervening mass. These distortions are called Einstein rings or Einstein arcs, and they are spectacularly beautiful. By studying these distortions carefully, measuring the positions and shapes of the arcs, we can map the distribution of mass in the cluster, including the dark matter that we cannot see directly. It is like doing invisible forensics, reconstructing the shape and location of something we cannot see from the shadows and distortions it creates in things we can see. These maps reveal that dark matter forms a smooth halo around galaxy clusters, extending far beyond the visible galaxies themselves. The distribution is different from that of ordinary matter, which tends to concentrate in the centers of galaxies where stars form. Dark matter is more diffuse, spread out in a larger halo. This difference provides important clues about the nature of dark matter. It must interact very weakly with ordinary matter and with itself, passing through regular matter like a ghost, like a neutrino streaming through the Earth, as if it were not there. This is why it has been so difficult to detect directly, despite decades of searching. Dark matter particles are streaming through your body right now. Billions of them every second, maybe trillions, but they pass through without interacting, without leaving any trace. Every particle in your body is transparent to dark matter, and dark matter is transparent to you. We coexist with it, but remain largely oblivious to its presence, like fish unaware of the water surrounding them. The search for dark matter connects to the broader question of what the universe is made of and how it came to be. The Big Bang theory, supported by extensive observational evidence from multiple independent sources, tells us that the universe began in an extremely hot and dense state about 13.8 billion years ago. But what does it mean to say the universe began? Was there a time before the Big Bang? What caused it? What, if anything, existed before? Did time itself begin at the Big Bang, or was there some kind of pre-existing state? These questions may be unanswerable, at least with current physics. The very concepts of time and causation might break down at the Big Bang. The singularity predicted by general relativity, where density and temperature and curvature all become infinite, represents a breakdown of our equations, a point where our theories stop making sense. Asking what came before might be like asking what is north of the North Pole. The question seems to make sense grammatically, but is actually meaningless because time itself might have begun with the Big Bang. There might be no before, no prior state, no cause in the usual sense. Some models suggest that time is emergent, that it does not exist at the most fundamental level, but emerges from more basic quantum processes. Others propose that the Big Bang was not the absolute beginning, but a transition from some prior state, perhaps a previous contracting universe, or a quantum fluctuation in a pre-existing multiverse. But these are highly speculative ideas, far from confirmed science. Yet this is deeply unsatisfying philosophically. Our minds rebel against the idea of an uncaused cause, a first moment with no prior moment. We are used to thinking in terms of causes and effects, of one thing leading to another, of every event having a prior cause. The idea that the entire universe, with all its matter and energy and the very fabric of space-time itself, simply began to exist without cause or explanation, challenges our fundamental intuitions about how reality works. Some physicists and philosophers propose that the universe came from nothing, that quantum fluctuations in a primordial vacuum could have triggered the Big Bang. Lawrence Krauss has written extensively about this idea, arguing that quantum mechanics allows for the creation of something from nothing, that the universe is the ultimate free lunch. But this just pushes the question back a step. Where did the quantum fluctuations come from? Where did the laws of quantum mechanics come from? Why do those laws have the particular mathematical form they do, rather than some other form? Why is there quantum mechanics rather than nothing? Others suggest that the universe is cyclical, that it undergoes endless cycles of expansion and contraction, big bangs and big crunches, repeating forever like a cosmic heartbeat. Roger Penrose has proposed a cyclic cosmology, where the universe goes through infinite aeons, each beginning with a big bang and ending when all matter has decayed and only photons remain. But this requires physics we do not yet understand and might violate the second law of thermodynamics. Each cycle should leave the universe with higher entropy than the previous cycle, eventually leading to a state of maximum entropy from which no further cycles are possible. And it still does not explain why there are cycles at all, rather than nothing. Still, others propose that our universe is just one of many in a vast multiverse, that universes are constantly being created through quantum processes or eternal cosmic inflation, and that we happen to find ourselves in one with properties that allow life to exist, because we could not exist in any other kind. This is called the anthropic principle, and it comes in weak and strong forms. The weak anthropic principle simply says that we should not be surprised to find ourselves in a universe compatible with our existence, because if it were not, we would not be here to observe it. The strong anthropic principle says that the universe must have properties that allow life to develop at some point in its history. This anthropic reasoning explains why our universe seems fine-tuned for life, without invoking a designer or special creation. There are about 30 physical constants in the standard model of particle physics and cosmology. Numbers like the strength of gravity, the mass of the electron, the cosmological constant, that have to have very specific values for stars and planets, and chemistry and life to be possible. Change any of them by more than a small amount, and you get a sterile universe with no structure, no complexity, no possibility of evolution or consciousness. Why do these constants have the values they do? The multiverse answer is that they do not have to. In a vast ensemble of universes with all possible values of the constants, we naturally find ourselves in one of the rare universes where the constants allow our existence. This is selection bias, observer bias. We are not typical observers in a typical universe. We are observers in the subset of universes capable of producing observers. But this is controversial. Some physicists and philosophers accept it as a legitimate scientific explanation. Others reject it as unscientific speculation, arguing that if other universes are unobservable in principle, then the multiverse hypothesis is unfalsifiable and therefore not science. Is it a legitimate scientific explanation or just speculation disguised as science? Can we ever know if other universes exist, if by definition we can never observe or interact with them? These deep questions about origins and ultimate explanations may lie forever beyond the reach of science. We can trace the history of the universe back to the Big Bang with increasing confidence and precision, but we may never know what caused the Big Bang or whether that question even makes sense. There might be a fundamental limit to explanation, a point beyond which we simply have to accept that things are the way they are, without further justification. An explanatory horizon analogous to the cosmic event horizon. This limit is reminiscent of the cosmic event horizon we discussed earlier. Just as there is a boundary in space beyond which we cannot observe or receive information, there might be a boundary in explanation beyond which we cannot go. The universe might be fundamentally mysterious at its core, knowable only up to a point, with ultimate questions remaining forever unanswered. This is both humbling and profound. It suggests that existence itself might be a brute fact, something that requires no explanation, because no explanation is possible, an irreducible mystery at the foundation of everything. In the first moments after the Big Bang, assuming the Big Bang was indeed the beginning, the universe was too hot for atoms to form. It was a sea of elementary particles and radiation, a quark-gluon plasma, at temperatures far exceeding anything we can create in particle accelerators, expanding and cooling rapidly as space itself expanded. The expansion was driven by the initial conditions of the Big Bang, and later by the energy density of radiation and matter. As the universe expanded and cooled, it went through several important transitions, phase transitions where the fundamental nature of matter and forces changed. First, about 1 microsecond after the Big Bang, when the temperature dropped below about 2 trillion degrees, quarks combined to form protons and neutrons through a process called hadronization. Before this, quarks and gluons moved freely in a hot plasma. After this, they were confined inside protons and neutrons and other hadrons. Then, about 3 minutes after the Big Bang, when the temperature dropped to about 1 billion degrees, protons and neutrons combined to form the lightest atomic nuclei through a process called Big Bang nucleosynthesis. This produced primarily hydrogen, about 75% by mass, and helium, about 25%, with trace amounts of deuterium, helium-3, and lithium. The abundance of these light elements matches theoretical predictions extremely well, providing one of the strongest pieces of evidence for the Big Bang theory. But the universe was still too hot for these nuclei to capture electrons and form neutral atoms. The temperature was still high enough that any electrons that combined with nuclei would immediately be knocked free again by energetic photons. The universe remained opaque to light, a glowing fog where photons constantly scattered off free electrons, unable to travel far before being absorbed and re-emitted. This is called the photon decoupling era, or recombination, though it is a misnomer since electrons and nuclei had never been combined before. About 380,000 years after the Big Bang, when the temperature dropped to about 3,000 degrees, the universe had cooled enough for electrons to combine with nuclei, forming neutral atoms for the first time. This moment, called recombination, or more accurately, first combination, made the universe transparent. Photons could suddenly travel freely through space without being scattered. The photons that were released at this moment have been traveling through space ever since, cooling as the universe expands, their wavelengths stretched by the expansion of space itself. Today, we detect them as the cosmic microwave background radiation, a faint glow that fills all of space with a temperature of about 2.7 degrees above absolute zero. This is the oldest light in the universe, a snapshot of what the cosmos looked like when it was just 380,000 years old, less than 1/30,000th of its current age. It is remarkably uniform, with the same temperature in every direction to within 1 part in 100,000. This uniformity was first measured precisely by the COBE satellite in the early 1990s, confirming a key prediction of the Big Bang theory. But the uniformity creates a problem. Regions of the sky that are very far apart, separated by more than 2 degrees on the sky, should have never been in causal contact. They are too far apart, and not enough time has passed for light to travel between them in the standard Big Bang model. So how did they reach the same temperature? How did they know to have the same properties if they could never have exchanged information? This is called the horizon problem, and it is one of several puzzles that motivated the theory of cosmic inflation. Another puzzle is the flatness problem. Why is the geometry of space so close to perfectly flat when this requires incredibly precise fine-tuning of the initial conditions? A third puzzle is the monopole problem. Why do we not see magnetic monopoles, which should have been produced in the early universe, according to particle physics theories? Cosmic inflation solves all these problems in one elegant stroke. The idea, proposed by Alan Guth in 1980 and refined by Andre Linde, Paul Steinhardt, and others, is that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, from about 10 to the power of negative 36 seconds to about 10 to the power of negative 32 seconds. During this brief moment, the universe expanded by a factor of at least 10 to the power of 26, growing from smaller than an atom to perhaps the size of a grapefruit or larger. This rapid expansion, driven by the potential energy of a hypothetical field called the inflaton, took a tiny region of space that was in thermal equilibrium and stretched it to become the entire observable universe. This explains the uniformity. The cosmic microwave background looks the same in all directions because all the regions we see came from the same tiny patch that had time to reach the same temperature before inflation. It explains the flatness. Inflation stretched space so much that any initial curvature was ironed out, like blowing up a balloon until its surface appears flat. It explains the lack of monopoles. Any monopoles that existed were diluted to undetectable densities by the expansion. But inflation does more than solve these problems. It explains the origin of structure in the universe, the seeds from which galaxies grew. During inflation, quantum fluctuations, tiny random variations at the subatomic level allowed by Heisenberg's uncertainty principle, were stretched to cosmic scales by the exponential expansion. These quantum fluctuations became classical density perturbations, regions where matter was slightly more or less dense than average. After inflation ended and the universe continued its more sedate expansion, these density perturbations grew under gravity. Denser regions attracted more matter, becoming denser still. Over hundreds of millions of years, these growing perturbations became the cosmic web of galaxies and galaxy clusters we see today. Every galaxy, every star, every planet, ultimately every atom in our bodies, can be traced back to quantum fluctuations that occurred during the inflationary epoch. Think about what this means. The galaxies, stars, planets, and ultimately life itself all grew from quantum fluctuations, from random microscopic variations that were amplified by cosmic inflation to macroscopic scales. In a sense, we owe our existence to quantum uncertainty, to the fundamental randomness built into the fabric of reality at the smallest scales by the Heisenberg uncertainty principle. Structure, complexity, order, organization, life, consciousness, all of these emerged from noise, from the quantum foam out of which the early universe condensed. This suggests a deep and beautiful connection between the very small and the very large, between quantum mechanics and cosmology, between the microscopic and the cosmic. The same processes that govern the behavior of individual atoms and subatomic particles also shaped the structure of the cosmos as a whole. The universe is not divided into separate realms, operating by different rules. It is a unified whole, where phenomena at all scales are interconnected and interdependent, where quantum effects on the smallest scales determine the structure of the universe on the largest scales. The predictions of inflation have been tested and confirmed. The pattern of temperature fluctuations in the cosmic microwave background matches the predictions of inflation incredibly well. The fluctuations are almost scale invariant, meaning they have similar amplitude at all scales, with a slight tilt exactly as inflation predicts. They are adiabatic, meaning the fluctuations in different types of matter are correlated in the way inflation predicts. They are Gaussian, meaning their statistical distribution follows a bell curve as expected from quantum fluctuations. Measurements by the Planck satellite and other experiments have measured the cosmic microwave background to exquisite precision, producing maps of temperature fluctuations accurate to better than 1 part in a million. These maps beautifully confirm the predictions of inflation and provide a treasure trove of information about the early universe. They tell us the age of the universe, the density of matter and dark energy, the rate of expansion, the geometry of space, all with unprecedented precision. If inflation is correct, and the evidence strongly suggests it is, it has profound implications for the nature of the universe and our place in it. The observable universe, everything we can see out to the cosmic event horizon, might be just a tiny bubble in a vastly larger cosmos. The total universe created by inflation could be trillions of times larger than what we can observe, perhaps infinite. In the eternal inflation scenario proposed by Andre Linde and others, inflation never completely ends, but continues forever in some regions of space, constantly creating new bubble universes. Other bubble universes might exist beyond our horizon, each with potentially different properties and physical laws, depending on how the inflaton field decayed and what vacuum state it settled into. The constants of physics, the masses of particles, even the number of dimensions of space might be different in different bubbles. We could never observe or interact with these other bubble universes, separated from us by vast distances and the cosmic event horizon, but they might exist nonetheless, created by the same inflationary process that created our own observable patch. This raises profound questions about our place in existence and the meaning of our lives. If there are infinite universes with all possible properties, does our existence require any special explanation? Are we just one random bubble among countless others, one roll of the cosmic dice? Or is there something special about our universe, some purpose or design or meaning that we have not yet understood? Is there any significance to our existence beyond what we create for ourselves? These questions connect to the deepest problems in philosophy, theology, and the meaning of life. Why is there something rather than nothing? Why does the universe exist at all? Does the universe have a purpose? Is there any meaning to existence beyond what we create for ourselves through our choices and actions? Does consciousness have any special significance in the cosmos? Or are we just a temporary pattern of matter and energy, no more meaningful than a wave on the ocean? Science can tell us how the universe works, how it evolved from the Big Bang to the present, how stars form and die, how planets coalesce from disks of dust and gas, how life emerges from chemistry through natural selection and evolution, how consciousness arises from neural networks processing information. But it cannot tell us why any of this happens, why there are laws of physics at all, rather than chaos or nothing, why the laws have the particular mathematical form they do, or whether existence has any ultimate meaning or value beyond what we assign to it. Perhaps these questions are beyond the scope of science, because they are not empirical questions. They cannot be answered by observation or experiment, by collecting data or testing hypotheses. They are philosophical or even religious questions that each person must answer for themselves, based on their own values, intuitions, experiences, and beliefs. Science can inform these answers, can provide context and constraints, but it cannot provide the answers themselves. Or perhaps they are simply unanswerable. mysteries that will remain forever beyond human comprehension, part of the unknowable core of reality that lies beyond the cosmic event horizon of explanation. Perhaps there are true facts about existence that we can never know, just as there are galaxies beyond our cosmic horizon that we can never observe. Perhaps reality has depths that human minds, products of evolution on one small planet, are incapable of fathoming. Yet even if ultimate meaning is unknowable, even if we can never answer the deepest why questions, there is profound value and meaning in the search itself. The mere fact that we can ask these questions, that we are conscious beings capable of contemplating our own existence and place in the cosmos, that we can ponder the nature of reality and wonder about meaning and purpose, is itself remarkable and perhaps even miraculous. We are the universe become aware of itself, matter organized in such a way that it can ponder its own origins and destiny, atoms contemplating atoms, the cosmos awakening to its own existence. This is not nothing. This is, in fact, quite literally everything from our perspective, because our perspective is all we have, all we can ever have. We are embedded in the universe, part of it, not separate observers looking in from outside. Every moment of wonder, every discovery, every act of love and creativity and meaning, making adds to the universe's richness and complexity. We do not need to know ultimate answers or achieve some cosmic purpose to find meaning and value. The journey itself, the exploration, the questioning, the seeking, the experiencing, all of this has intrinsic value. We are participants in the grand cosmic story, brief, flickering patterns of consciousness in an unimaginably vast and ancient universe, but participants nonetheless. Human consciousness, this strange emergent property of matter, organized in particular ways, this ability to be aware, to experience, to feel and think and wonder, might be the most remarkable phenomenon in the entire cosmos. As far as we know, and we have looked fairly carefully, consciousness seems to be rare in the universe. Most matter exists in stars and gas clouds, unconscious, unaware. Life itself may be rare. Intelligent life capable of asking questions about existence may be rarer still. This makes each moment of conscious experience precious beyond measure. You, reading or hearing these words, thinking these thoughts, experiencing this moment, are one of the universe's rare treasures, a brief flowering of awareness and meaning in a cosmos that is mostly dark and silent and unconscious. Your existence, however brief in cosmic terms, however small in spatial scale, is a triumph over entropy and meaninglessness. The speed of light, which seemed like such a limitation at first, such a barrier preventing us from exploring the cosmos and connecting with other civilizations, becomes a feature rather than a bug when viewed from this perspective. It ensures that the universe remains full of mystery and possibility, that there will always be new frontiers to explore, new questions to ask, new wonders to discover. It preserves diversity by preventing everything from homogenizing into one uniform whole. It creates islands of independent evolution, separate branches of the cosmic story. The cosmic event horizon, that boundary beyond which galaxies recede faster than light, creates a natural limit to our knowledge, but also a profound reminder of our place in the cosmos and the limits of what we can know. We are finite beings in a possibly infinite universe, conscious observers in a vast unconscious expanse, seekers of meaning in a realm that operates according to mathematical laws, without inherent purpose or intention. Yet within those constraints, we have managed to peer billions of light years into space, to understand the fundamental forces that govern reality, to trace our own origins back to the Big Bang itself, and beyond to cosmic inflation. The nomadic civilizations that might one day venture into the cosmos, if such a thing ever becomes possible, would face challenges we can barely imagine. They would develop their own cultures, their own languages, their own ways of understanding reality, shaped by their unique experiences and environments. They would remain connected by their shared human heritage and their common origin on Earth, but they would diverge in ways that would make them almost unrecognizable to their ancestors over enough time. Some nomads might choose to settle on worlds they discover, founding new civilizations that blend human culture with local conditions and perhaps with any native life they encounter. These settlements could become stepping stones for future explorers, way stations in the vast darkness between stars. But they would also become isolated from each other by the vast distances and time delays of interstellar space, separated by years or centuries of communication lag. Humanity could fragment into countless separate branches, each adapted to their local environment through natural selection and genetic drift, and perhaps genetic engineering, each following their own evolutionary path toward an unknown future. This fragmentation might seem tragic from one perspective, the breaking of human unity into isolated tribes that can barely communicate. But it is also beautiful when viewed another way. It represents the ultimate flowering of human potential, the spread of consciousness and intelligence and meaning throughout the galaxy, and perhaps beyond. Each branch of humanity becomes an experiment in what it means to be alive, to be aware, to be part of the cosmic story. Different environments and challenges would lead to different solutions, different cultures, different philosophies, different ways of being human or post-human. The diversity of human experience would explode across the galaxy, creating a richness and complexity of conscious life that could never emerge in one isolated biosphere. And through it all, the universe continues its own evolution independent of what humans do. Stars are born in collapsing clouds of gas and dust, igniting when temperature and pressure become high enough for nuclear fusion. They live for millions or billions of years, depending on their mass, fusing hydrogen into helium and helium into carbon, oxygen, and heavier elements. Massive stars end their lives in spectacular supernova explosions, scattering heavy elements across space and sometimes leaving behind neutron stars or black holes. Galaxies collide and merge in slow motion, cosmic dances spanning billions of years, transforming spiral galaxies into elliptical galaxies, triggering bursts of star formation as gas clouds collide and compress. The cosmic web of dark matter continues to grow and evolve under gravity, with structure formation proceeding from smaller to larger scales in a hierarchical process. The relativistic travelers, if they exist, would witness this evolution firsthand, becoming chroniclers of cosmic history on scales that dwarf human civilization. They would see stellar nurseries where new stars ignite in the hearts of giant molecular clouds, planetary systems forming from disks of dust and gas around young stars, civilizations rising and falling on countless worlds, galaxies transforming over billions of years from their perspective, though only decades pass aboard their ships. They would carry with them the memories and knowledge of countless worlds, connecting disparate branches of humanity and other intelligent species through their journeys, serving as living bridges across the cosmic void, proof that consciousness can persist and spread, even in the face of the universe's vast indifference and the tyranny of the speed of light. They would be living encyclopedias, repositories of information about civilizations that might no longer exist by the time anyone receives their messages. But what about the average person who will never journey to the stars? who will live their entire life on Earth, or perhaps in our solar system, if human expansion reaches that far. Does this cosmic perspective, this awareness of the vast universe beyond our reach, the recognition of our tiny place in the grand scheme of things, diminish the importance of everyday life? Does it make human concerns seem trivial and meaningless? Quite the opposite when viewed correctly. Understanding our place in the universe makes every moment more precious, not less. We are patterns of organized complexity in a universe that trends toward disorder and maximum entropy. We are nodes of consciousness in a cosmos that is mostly unconscious, dead, unaware. We are meaning-making creatures in a reality that operates according to blind physical laws, without inherent purpose or intention or care. Every conversation we have, every relationship we build, every connection we make with another conscious being, every work of art we create, every scientific discovery we make, every problem we solve, every act of kindness we perform, every moment of joy or wonder or love we experience. These are all acts of defiance against entropy and meaninglessness. They are assertions that consciousness and meaning matter, that the universe is richer and better, because we are here to observe it and ponder it and celebrate it and imbue it with significance. The fact that the universe is so vast and we are so small does not diminish us. It elevates us. Against all odds, in a cosmos that is mostly hostile to life, on a small, rocky planet, orbiting an average star in an ordinary galaxy, matter has organized itself into patterns that can think and feel and wonder. We are the universe's way of knowing itself, the cosmos awakening to its own existence, reality becoming self-aware through our minds. When you look up at the night sky and consider that the light from distant stars has traveled for years or centuries or millennia to reach your eyes, you are engaging in a form of time travel, directly observing the past. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, they are observing the universe as it was just 380,000 years after its birth, seeing photons that have been traveling for nearly 14 billion years. When they peer at the most distant galaxies with powerful telescopes, like the James Webb Space Telescope, they are seeing light that has been traveling for over 13 billion years, showing us the universe when it was less than 1 billion years old, when the first galaxies were forming, and the first generation of stars was lighting up the darkness. These are not artists' conceptions or simulations. These are real observations, direct views into the deep past. This ability to look back in time allows us to reconstruct the history of everything, to trace the evolution of the universe from a hot, dense state to the complex cosmos we see today. We can watch galaxies form and evolve through cosmic time. We can see how stars have changed over billions of years. We can observe the chemical enrichment of the universe as successive generations of stars create heavier elements and scatter them through space. We can even make predictions about the future based on our understanding of cosmic evolution and the accelerating expansion. Based on observations of distant supernovae and measurements of the cosmic expansion rate, we know that the universe will continue to expand forever, growing colder and more diffuse as galaxies move farther apart, diluted by the relentless expansion of space. In the far future, trillions of years from now, the night sky will be very different for any civilizations that exist then. Most galaxies will have receded beyond the cosmic event horizon, becoming forever unreachable and unobservable, their light stretched to infinite wavelengths by the expansion. Civilizations that arise in that distant era will see a much emptier universe, perhaps just their own galaxy or local group, if those have merged. They might not even realize that other galaxies exist, or that the universe is expanding. because all evidence of it will have vanished beyond the horizon. They will live in an island universe, isolated and alone, with no way to know about the rich cosmic history that came before. No way to learn about the Big Bang, or cosmic inflation, or the cosmic web that we can still observe. This makes our current epoch special, perhaps uniquely privileged. We live at a time when the universe is old enough to have formed complex structures like galaxies and stars and planets and life, and intelligent observers, but young enough that we can still see the evidence of cosmic evolution spread across the sky. We can still observe the cosmic microwave background, still see distant galaxies, still measure the expansion and learn about the early universe. We are privileged observers, living at a cosmic moment when the universe reveals its secrets most clearly. Future civilizations might envy us our view of the cosmos, our window into cosmic history, just as we might envy future travelers their ability to explore it directly if such technology ever becomes possible. We live in what might be called the golden age of cosmology, when the universe is observable and comprehensible, when evidence of its history is still visible and measurable. The nature of dark matter remains one of the great unsolved mysteries in cosmology, despite decades of research. We know it exists because of its gravitational effects on visible matter, on the rotation of galaxies, on the motion of galaxy clusters, on gravitational lensing, on the cosmic microwave background, on structure formation. Multiple independent lines of evidence all point to the same conclusion. But we have not yet directly detected dark matter particles or determined their nature. It makes up about 27% of the universe's total mass and energy, far outweighing the ordinary matter that makes up stars and planets and people by a factor of about 5 to 1. The remaining 68% of the universe is dark energy. This means that everything we can see and touch and measure directly, all the atoms in all the stars and planets and living things, all the baryonic matter studied in all our laboratories and colliders, makes up less than 5% of the universe. We are, in a very real sense, living in a universe we barely understand, made mostly of substances we cannot see or touch. 95% of the universe is dark to us, invisible, mysterious, known only through subtle, indirect effects. Yet, through careful observation and clever reasoning, we can infer the existence of these hidden components and study their effects on the visible universe. This is the power of science: to deduce the invisible from the visible, to infer reality from evidence. The cosmic web that dark matter forms provides the scaffolding on which galaxies grow and structure develops. Dark matter's gravity pulls ordinary matter together, allowing clouds of hydrogen and helium to collapse and form stars through gravitational instability. Without dark matter, galaxies as we know them could not exist. The universe would be a very different and much emptier place, perhaps with only small dwarf galaxies, or no galaxies at all. Just diffuse gas slowly collapsing under its own gravity. Understanding dark matter is not just an academic exercise or a puzzle for physicists to solve. It is key to understanding how the universe works at its most fundamental level. How structure forms, how galaxies evolve, perhaps even how the universe will end. Dark matter shaped cosmic evolution and continues to shape it today. We are products of that evolution, our very existence dependent on dark matter's role in structure formation. Observations of galaxy clusters, where hundreds or thousands of galaxies are bound together by gravity with masses of 10 to the power of 14 or 15 solar masses, reveal the presence of dark matter through gravitational lensing. The technique is elegant in its simplicity. Just as a glass lens bends light through refraction, when light passes from one medium to another. The gravity of massive objects bends the path of light, traveling near them through the curvature of spacetime, predicted by general relativity. When we look at distant galaxy clusters, we see distorted images of even more distant galaxies behind them, stretched into arcs and rings and multiple images by the gravitational field of the intervening mass, acting as a cosmic lens. The most massive clusters can create complete Einstein rings, where a background galaxy is lensed into a perfect circle around the cluster. These are among the most beautiful phenomena in astronomy. Geometric demonstrations of Einstein's theory, visible across billions of light years. By studying these distortions carefully, measuring the positions and shapes and brightnesses of the arcs and multiple images, we can map the distribution of mass in the cluster, including the dark matter that we cannot see directly. It is like reconstructing the shape of an invisible lens from the distortions it creates in images viewed through it. Sophisticated computer models can invert the lensing signal to produce detailed maps of dark matter distribution. These maps reveal that dark matter forms a smooth halo around galaxy clusters, extending far beyond the visible galaxies themselves, sometimes 2 or 3 times farther than the most distant visible galaxy in the cluster. The distribution is different from that of ordinary matter, which tends to concentrate in the centers of galaxies where stars form. Dark matter is more diffuse, spread out in a larger, more extended halo, dominating the mass on large scales. This difference provides important clues about the nature of dark matter. It must interact very weakly with ordinary matter and with itself, or it would collapse into dense clumps at galaxy centers, just like ordinary matter does. It must be collisionless or nearly so, passing through itself and through ordinary matter like a ghost. This is why it has been so difficult to detect directly, despite decades of effort and ever more sensitive experiments. Dark matter particles are streaming through your body right now, as you exist here on Earth. Billions or trillions of them every second, depending on their mass and abundance. But they pass through without interacting, without leaving any detectable trace. Every particle in your body, every atom, is transparent to dark matter, and dark matter is transparent to you. We coexist with it, swimming in an invisible ocean of dark matter, but remain largely oblivious to its presence, except through its gravitational effects on large scales. The search continues in laboratories around the world. Underground detectors shielded from cosmic rays by kilometers of rock wait patiently for the rare collision of a dark matter particle with an atomic nucleus. Satellite experiments search the sky for gamma rays or other signals from dark matter particles annihilating each other. Particle colliders try to create dark matter particles by smashing protons together at high energies. So far, definitive detection remains elusive, but the search continues with ever more sensitive instruments and clever experimental designs. Meanwhile, the universe continues its relentless expansion, driven by dark energy, stretching the fabric of space itself and carrying galaxies apart. Every second, space expands. Every moment, the cosmic event horizon creeps closer, swallowing more galaxies into the unreachable beyond. We stand at a unique moment in cosmic history, able to observe and understand a universe that is slowly fading from view, losing information and structure to the accelerating expansion. Future generations, if any exist, will inherit an increasingly empty cosmos. The galaxies we see today will be gone, receded beyond the horizon. The cosmic microwave background will fade and cool. The evidence of the Big Bang will slowly disappear. Astronomers of the far future will face an impoverished universe with fewer clues to its history and origin. But we are here now, at this moment, with the universe spread before us like an open book. We can read its history in the cosmic microwave background, in the light of distant galaxies, in the gravitational waves from colliding black holes, in the abundances of light elements. We can trace the evolution from the Big Bang through inflation, through recombination, through dark ages, through the first stars and galaxies, through billions of years of cosmic evolution to the present day. We are the universe understanding itself, matter pondering its own origins, consciousness emerging from unconsciousness to ask why and how and what does it all mean. This is our privilege and our burden, our joy and our responsibility. We are the custodians of knowledge in a universe that is slowly forgetting itself, the keepers of cosmic history in an expanding cosmos that erases its own past. And so we observe, we measure, we calculate, we theorize, we build ever more powerful instruments to peer deeper into space and further back in time. We search for understanding, for meaning, for connection across the cosmic void. We tell stories about the universe and our place in it, creating narratives that give structure and significance to our brief existence. The edge of everything that NASA and other space agencies have mapped is not a final boundary, but an invitation, a challenge, a reminder that there is always more to discover, always deeper mysteries waiting to be explored. Each answer we find generates new questions, deeper and more subtle than before. This is the nature of science and human curiosity, an endless frontier of discovery, where each peak climbed reveals new peaks beyond, each horizon crossed reveals new horizons ahead. The universe will always have more secrets to reveal to those patient and clever and curious enough to seek them out, more wonders waiting to be discovered, more mysteries waiting to be solved. We may never reach the final answers, may never climb the ultimate peak or cross the final horizon. The universe may be inexhaustible in its depth and complexity, always offering new challenges to those who seek to understand it. But the journey itself has meaning and value. The search for understanding, the pursuit of knowledge, the wonder and awe we feel when contemplating the cosmos, these are among the highest expressions of human consciousness and creativity. We are meaning-making creatures in a universe that does not come with built-in meaning. And so we create it through our efforts to understand, to explore, to connect, to matter. Every moment we spend pondering these deep questions, every effort we make to push back the boundaries of the unknown, every discovery we make about the nature of reality, adds something precious to the universe. We are participants in the cosmic story, not just observers. Our consciousness, our curiosity, our capacity for wonder and understanding, these make the universe richer and more complete than it would be without us. So we continue the search, continue the exploration, continue asking questions and seeking answers, knowing that the journey has no end, that the mysteries are inexhaustible, that the universe will always have more to teach us. And in that endless search, in that perpetual journey toward understanding, we find meaning and purpose and connection. We find our place in the cosmos. We find ourselves.